great. That's the thing I was hoping for. Okay.
Yeah. So we'll start.
That's okay. That's fine. At this stage of the game and this part of the video call, it's basically what you want to show us. I don't know if you've done slides, if you've done or whatever, but the basic thing of the review is to see where you're at rocket wise, contest wise, and then we'll probably be asking questions. I'll be very curious to know how you're doing your reefing system, since that's going to be a major part of recovery. And then we'll go from there. Also, we'll be very curious to know if you've got your contest motor reload. I know you got your case. I don't know if you've got your motor reload or not yet. So I'll turn it over to you, and then we'll go from there.
Okay. Yeah, we've created a basic PowerPoint that will just describe about our rocket. And at the end of the presentation, you guys can ask questions. Is that cool? Okay, I will just share my screen. Okay, yes. Yep.
Wow.
Yeah. Okay. Okay. Yeah. So welcome everyone. Good morning. Well, it's evening for us. So yeah, we are Team 53, Thrust MIT from Manipal Institute of Technology, India. And this is our presentation. So we are partaking in the 10K COTS category this year as well, same as last year. And before we continue, I'll just quickly introduce everyone here. So I'm Ashwin Raj. I am the team leader of Thrust MIT this year. And on my right, I have Asta. She's a structures head. And on my left, I have Pranav, who's a senior payload member. And we have Avionics head, who's Ronan. Yeah. And we have a senior aerodynamics member, Kaza. And we have Arjun Chabra, who's the diving lead. Okay, so we'll start. So this year's rocket is called Altair. I'll just quickly go over the basic stats of a rocket. We've also included air brakes this year. I'll talk more about it later. But air brakes, we've worked on it for several years, and this year we're finally confident enough to go ahead with it. So these are the basic stats of a rocket. Its diameter is 5.9 inch. Its wet mass around 66 pounds. And our predicted apogee is around 10,384 feet. Now, this is including the air brakes after it's deployed, which will be deployed only after the motor burnout phase. So yeah, moving on to the aerostructures. Asta will take over.
Hi. Altair's airframe consists of 3 body tubes, out of which recovery, motorway are made out of carbon fiber, and the midway is manufactured using GF to enable telemetry in our avionics and payload.
Yeah. And we have an aero cover. Now, this is basically just to house a pitot tube and a run cam, a camera. This is 3D printed. It's made of ABS. It looks something like this. Yeah, we've 3D printed it. And we have 2 of them. They are placed diametrically opposite. It's somewhere in the avionics bay. And since we're using air brakes, we want proper velocity values. So we have a pitot tube. The height of the pitot tube was properly calculated using boundary layer height, using CFD simulations and other simulations which we ran. So yeah. The fin design. Now, last year, for our previous rocket that the previous batch did, we tried something new with our fins. It's called a leading edge extended fin. So this basically helps improve the aerodynamic efficiency of our rocket. We've further dwelled into the design. We've made it sort of even better with the curves of the fins. So the stats of the fins are given. And fin flutter was very important for this year's fin design. And after calculating the fin flutter velocity, which comes to around 1600 feet per second, and considering a factor of safety of 1.5, we are getting a safe flight velocity of around 1050 feet per second. Now it's still above our rocket's top speed, so our fins won't flutter and it won't resonate. And moving on to propulsion, we are reusing our last year's rocket, which is the M3400 rocket, specific total impulse of 9,994 Newton seconds, maximum thrust of around 4,000 Newtons, and it has a burn time of around 3 minutes. We decided to reuse this because we recovered this successfully last year, the motor head and the casing. We did some NDT tests, non-destructive tests, and like the X-rays and stuff, and we determined it fit for another launch. So yeah, we saved some cost in this aspect. Recovery, now Kader will take over.
So this year, we were planning on going with tender descender, but we couldn't get any flight tests done. So we stuck with our old method of using a single parachute, but dual event. So the parachute is bought from Fruity Shoots because we had some material constraints. Now the same parachute, it's 120 inch in diameter, and we are using it as a drogue chute in the reef condition. This drogue chute is ejected at apogee, and once it reaches around 1500 feet, it's disreefed. So based on all the calculations for terminal velocity, we have come to a ground hit velocity of about 6 meters per second or 20 feet per second. And the parachute is protected with the help of a parachute liner to protect it from the hot gases. And the shock cords are lengthy enough so that, and we've made sure that when we fold the parachute, it does not get entangled. And yeah, that's pretty much it. Moving on to avionics, Ronan will take over.
So the avionics in Altair comprises of 4 different systems. One is the primary flight computer that we have, which is going to do a lot of stuff with the air brakes. It's the only computer on board which does active controls, and it, along with active controls, it also does recovery events where it deploys the drogue at apogee and then disreefs the parachute at 1,500 feet above ground level. Now, the secondary SRAD flight computer that we've built is mainly surface mount technology, which is what we are trying out for the first time, and we are just testing the flight computer in the launch. For redundancy, we've used the RRC3 by Missile Works, which is again configured to deploy the drogue chute at apogee and then disreef the parachute at 1,500 feet above ground level. Now, now we've made sure that there is some sort of delay between the two lines so that we understand whether the COTS or the SRAD worked for our events. Also for GPS, we've made sure that there's both SRAD and COTS GPS. The COTS GPS we're using is the featherweight GPS. The SRAD GPS that we have is made by Adafruit. It's the Adafruit Ultimate GPS. And the data is sent over via a 2.4 gigahertz Wi-Fi module, which we have on board. For the flight camera, we decided to go with the RunCam Split 3 as it has good amounts of quality in terms of video quality and in terms of storage as well. For the active controls, what we've done is we have a prediction algorithm which predicts the apogee of the rocket beforehand. And based on the set point, we deploy the air brakes on the rocket using the primary flight computer. We've also developed a ground station which runs on the Teensy 4.1 and has an XB Pro module over there, which gets in the telemetry data from the rocket and gives us a visual representation of how the rocket is going to fly. That is possible through our SRAD plotter, which we've been developing for the last 2 years. Moving over to payload, I'll just hand it over to Pranav.
Yeah. Firstly, good morning, everybody. And this year we're using a 4U CubeSat payload of 4.2 kilograms. the main technical aspect for this year's payload experiment is its attitude control of 3DF parallel manipulator under extreme high vibrations and g-forces it experiences during its flight and during the change of orientation at apogee. The major work that has not happened in the past with our team and it is going to happen with our team is that we are going to visually and data log the whole flight data when the demonstration of the experiment is taking place with the help of a camera on board and an XD card on board. The materials used were aluminium for the whole because of its excellent structural strength and lesser weight. Yeah, and the every hand calculation for the Stewart platform based mechanism is been hand calculated and verified with the help of an MPU sensor. Yeah, moving on, we can go to air brakes, I guess. To hand over to Ash.
Asta will take it.
As Ashwin mentioned before, we have been working on the air brakes mechanism for quite some time, and this year we are finally implementing it in our rocket. They're designed to deploy when the four main conditions are being fulfilled. The rocket should not be in the boosting phase. The apogee should be up more than 5,000 feet, and the speed of the rocket should be under 262 feet per second. Also, the apogee predicted by the flight computer should be overshooting the previously set apogee. The mechanics part of the air brakes is based on a slider crank mechanism where and it's powered by a high powered torque servo motor. It also includes a spring retraction mechanism to prevent any failure in case of power loss.
Okay, and lastly, this is ConOps. I'll just run over all the events that our rocket encounters. So you have the liftoff, you have the power descent, you have the coasting phase, you have the apogee, the ejection, parachute ejection in drogue, and then you have the disreefing. So after liftoff, the motor burns for 3 seconds, and you're in the powered coasting phase. And once the 3 seconds is over, once the motor is burnt, then you reach the coasting phase. And here is where the air brakes can be deployed. Now it will be deployed based on how much apogee we're hitting, predicting. Based on that, the air brakes will deploy. And once at apogee, the piston cylinder, our ejection mechanism will fire and our parachute will be ejected. It will be ejected in the drogue state or the reef state. And once the flight computer detects that the altitude is around 1,500 feet, the parachute is disreefed and then the main chute is out. And then it recovers at a ground velocity of around 20 feet per second. And yeah, that marks the end of our presentation. You guys have any questions? Go ahead.
Yeah, a couple. First of all, I want to compliment you on an excellent presentation. You actually answered a couple questions that I had, so that's one less thing to go through. Can you just do a quick scan, show me the rocket?
Well, our body tubes are not here yet. We've given them for paint, but we can, due to like local elections and all in this state, it's pretty wild out here. But we can show you the other parts of it. Arjun, can you just?
Okay, that's fine.
Yeah. So you can see. Yeah, so that is our motor bay assembly over there. Arjun, show
Okay,
them.
can you do me a favor and close out your
Oh,
presentation?
right. Yeah, one.
That way the video is
Yep.
a lot clearer. There we go.
Okay. Yeah, so this is our motor bay assembly. You can see the fins. They're welded to the stringers just like last time. It did pretty well last year, so we went ahead with it this year as well. And there are the centering rings, and we have a damper between the thrust plate and yeah. Arjun, you can just show them the bottom. And there's a retainer at the bottom as well. Yeah.
Okay, you made your own tubes. Do you have any examples of your
Yeah,
airframe?
body cubes you can see. Show them that one. This one. So this is a sample one. We got one of them. There's still two more left to come. So we have a metal coupler here with the air brake slots. Yeah. This is carbon fiber tube. It's this is where basically the motor part of it will sit in. We have to make the slots for the fins as well. It's remaining. But yeah, our glass fiber tubes, they've gone out for the varnish and the paint. They'll come soon. And our nose cone, you can show nose cone. Yeah, nose cone with the nose strip.
Okay,
It's kept on a sample tube right now, but yeah.
okay, so you definitely have some construction
Yeah, yeah,
ahead
yeah.
of you.
We do it.
Yeah. What in terms of school, are you still in finals? Are you at a break?
No, our finals are next week. So
You're
we're trying to just finish everything this week and then go for our finals. Yeah.
Okay, all right. In terms of the reload for the motor,
Yeah.
do you already have that?
Yeah,
Or
yeah,
you
we have. We're getting from offwegorocketry.com. Mr. Gary, he sorted out us like last time, and we've made the payments and everything is done. He said he'll bring it.
okay? Just want to double check to be sure.
Yeah.
Okay. I like the safety that you put into the air brakes, with the spring and all that for retraction, not activating until 5,000 feet and so on and so forth. Those are all really good safety rules. And, you know, to make sure, my main concern is air brakes under thrust, which you have totally just taken away from the table. So perfect. Okay. Well, I'm a little bit confused. Not well, confused, or I can't visualize it in my mind. Let's put it that way. Do you have any good slides, pictures, diagrams of the reefing system and how the electronics is supported?
Well, we can show it to you right now. Bring the show the parachute and the reefing lines. I'll show you a diagram as well. I just draw one out.
It's there in
Is it the same as last year?
Yeah,
basically?
same as last year. But last year we put a parachute in a parachute liner this time. Yeah. Oh no.
Did it work last year, Bob?
Okay.
I think so. I can't remember, honestly.
Yeah, okay. Well, as a team,
okay, just
did the
take it up.
reefing system work last year?
Okay, yeah, that's good enough. Okay, yeah. Just zoom in on the hoops. Okay, so if you can see the metal hoops around the skirt, so we stitched about 5 of them, alternating 6 of them, sorry, in alternating gores. And this is where our reefing lines will go. Now they're the same lines as the sort of suspension lines you can see. They're similar to it. And at the end of one of them, we will have our reefing cutter, which the Piranha line cutters we got. Kadir, do you have the Piranha line cutters? Yeah.
Piranha line cutter.
Yeah, the L3 one.
Okay. Do you have one or two?
We have two. We have one for
Okay.
redundancy. Yeah. And it's not here. Okay. Well, oops. Okay, so we have the Piranha line cutters attached to two ends diametrically opposite, and the lines pass through that. Now we have those long reefing wires that Kadir is stepping on. Oh, Kadir, pick the reefing wires. Yeah. Okay, so these two ends of it goes to two ends of the reefing cutters, and the other end goes straight through the parachute and into the avionics mount over here. Through the bulkhead. Yeah, through the recovery bulkhead as well. And it's hard to visualize right now. But yeah, we have a recovery bulkhead here. So the wires will go through one of these holes, and the other hole is for the eyeboard. Yeah, one for the eyeboard, one for the reefing wire. Now this sits. Oh, you have. Yeah. Okay, so it sits something like this. You can sort of imagine it. And the wires, they go to the SRAD flight computer and the RRC. And once it's time to reef, it will send the signal to reef. Yeah. Now we made sure that it won't tangle as well. We have swivels attached to it too. I'll show the swivel. It attached here.
Okay,
Okay.
that helps, and thank you.
Okay.
So the wire that actually triggers the cable cutter is controlled by the altimeters within the electronics bay.
Yeah, which is right below.
Which means you have a very long run
Yeah.
from the electronics bay up to the line cutter, correct?
Yeah.
How do you protect that wire to make sure it doesn't
Now,
get broken?
yeah, the wires are inside those nylon sleeves. So we think we've done plenty of ejection tests and reefing tests too, and these wires have sustained long enough. If we do see some marks on it, we'll buy new nylon sleeves to protect the wires. But yeah, now they've survived long enough. But yeah, we will do a couple of ejection tests soon, as in like we have 2 more left to do. And if these wires are still fit, we'll use them. Else, we are getting new nylon sleeves to fit this wire.
What gauge is the wire?
What? Excuse me?
What gauge is the wire? Do you know?
17. 17 AWG.
So, can you describe last year, and since you're using the same basic setup, how last year worked?
Well, our last year's recovery didn't go so successful. We did crash. We got our predicted apogee almost to the dot, but then the recovery wasn't so successful because the parachute couldn't come out. Now we know for a fact that our ejection did happen, but I think the parachute was too tightly packed. So last year we had a stitched parachute, which we were using for the past 2 years, as in 2 years prior to last year. And it was much thicker, and we had thicker shock cords and everything. But so we realized that, and it was hard to fold as well. It was thick, the material was thick. So we realized that, and we decided to buy a parachute this year from Fruity Shoots, the COTS parachute, 120 inch. Yeah. So, and this package is much better. Yeah.
It's coming back to me now. I recommended they change the way they were folding their chute, and I think I might have even recommended they change shock cord material. And that was a last minute change, and it was a very tight fit. And if their recovery system failed, it was because of that last minute change and the tight fit. So that was on me.
Okay. There's no way you can test this before you launch it, right?
Yeah, we can't do a flight test. We can
can't
do
do a
multiple
flight.
ground tests, but it's hard to get permission out here.
Yeah.
Okay. Now, explain to me the electronics hookup and what is controlling and how you're controlling the cable cutters.
The electronics part. Yeah, Ronan will take it.
So for the ejection charges, we have 2 flight computers. One is this is the primary SRAD over here, which has a static pressure sensor, and we determine the apogee by taking a difference in pressure. One is this, and for a redundancy, we have our RRC3s mounted here, which both of them are isolated systems, and we are going to be sending a charge from this both at drogue and main deployments. So this one sends a charge at apogee, which is again determined by our algorithm. This one is a commercially manufactured altimeter, which has been through certain tests. We've done vacuum jar tests on both of these altimeters and the SRAD primary flight computer as well. This is the flight computer which also does active controls and predicts our apogee and handles the entire air brakes and all of the other events.
Okay, all right, so the missile works, okay, then you're, okay, so you have two cable cutters. That means the missile works is hooked up to one of them and your SRAD is hooked up to the other one?
Yeah.
Okay. All right, and they're commercial cable cutters.
Yeah.
We're in good shape there. Okay, all right. Okay, my main concern on this is going to be the long wire run, you know, but it is what it is, I guess, on that end of it. I will say you have very unique fin design.
Yep.
It's the first time I've seen that one. But hey, if it works out, it works out.
Yeah. It's worked out
the-
last time too, and we've made it better. We have better efficiency this time. So
Cool. You've covered everything that I had a real concern about, which was obviously air brakes and reef parachutes. You did a study that if the reefing doesn't occur, do you know what your descent rate? Your descent rate would be your drogue rate, which would be roughly what, 80 feet per second or whatever.
75. Yeah.
Yeah, 75 feet per second. Okay, it's a little slow, but that's okay. I'm not gonna worry about that. You have some building to do.
Yeah, it should be done by this week.
Oh, okay, cool. Lee, you got any questions and Bob, follow up also?
I might have missed it, but how do you initially deploy your parachute? Was that a black powder charge?
Yeah. We have the 4F black powder. Once the apogee is detected, so it sort of builds pressure into. So inside here, you'll have your E-match, and inside here, you will have your sort of black chart sitting in with the E-match over here. That'll be connected to your flight computer. So once the apogee is detected, it sends charge to the E-match, and then it builds pressure and pushes it out and pushes the parachute out. And the nose cone is held through shear pins. So it breaks the shear pins, and yeah, it is ejected.
Okay. How much black powder do you plan to use?
We're planning to put around 5 grams.
And
we've done calculations. Yeah, it comes around 4 to 5 grams.
The piston that you're pushing off, can I see a close-up of that? Hold it up there. So you have the piece on top that's coming off?
Yeah.
Can you show that on the camera?
Yep.
So yeah, that piece right there. How does that piece, is that piece tied to something?
Yeah. So there is a hole over here. Can you see this hole?
Yep.
Yeah, so
we'll
tie to the idler. Can you repeat?
Different.
How long is, so there's a string or a tether tying to that. How long is that?
Roughly it'll be like 50 centimeters, almost. Like 50 centimeters. It's long enough for it to sort of push it out and.
Okay, 5 grams. What type of shear pins are you using and how many?
The nylon. It'll be M4 nylon shear pins. Or
10 of the 440 nylon?
What? Which was the number again? Of nylon shear pins. 254. Or M4. Either of them works. Oh. Yeah, I'm not exactly sure of the make of the nylon, but see them. Ask M4. M4 it is. Do we have one?
So how many of the pins?
Four of them. Four.
Okay.
We've done ejection tests. It's always broken.
Yeah.
Okay.
Have you actually? Well, I guess the rocket's not together yet. Do you plan on ground testing?
We've done ground testing. Yeah. So once the body tubes come, we're going to do integrated tests with the entire rocket build. So we've done ejection tests with just the parachute and just the recovery base setup, essentially with the nose cone and shear pins.
Okay.
So once
all right,
everything is ready, we'll do with the entire rocket.
Bob, any other questions?
I do have some questions. So on your deployment charge, I guess you don't have a backup. There's just one one altimeter with 2 E-matches in the black powder?
Yeah.
Okay.
Hmm,
Um,
that may be a problem.
yeah, I'm not crazy about that piston. I think it's an idea that, you know, I don't want to shoot down. Would like you to try, but I'm not sure the value that adds. But we can talk more about that, I guess, at Spaceport.
I'm
Yeah,
I'm
I
aware
believe-
of those concerns. Yeah, even previous batches, they have had similar issues, but we've done multiple ground tests, like multiple. We've done at least 8 to 10,
Well,
and we have a high success rate. Again, we're planning to do few more with the entire rocket, and I'm very confident that it
How's the piston held on
Well-
to the
so it's a
surface?
very
How is it?
tight fit. It's like an interference fit. So once
Very
everything
tight.
is sealed off, it's a pretty good.
Friction.
Okay. One of the concerns is at burnout, you'll have a lot of negative G's taking it the other direction. And if it comes off or comes loose, your black powder is not going to be tightly packed, and it could fail in that way.
That's a concern.
Something to think about.
Yeah.
But we made sure that it's properly sealed, so it's a proper vacuum inside. But yeah,
Yeah.
that's a valid concern.
Yeah, the thing, according to the rules, you really need 2 ejection charges. Not just 1. And 2 E-matches don't meet the definition of redundancy because you only have 1 charge size.
Oh, yeah, we have 2 igniters. We have 2 E-matches.
But no, the E-matches do not blow things apart. It's the black powder.
Right.
So the recommended dual deployment for apogee and even for mains is, and you've already covered with your roofing system, you've got 2 cable cutters, right? Okay, we need to do the same thing at apogee with 2 independent charge wells, one hooked up to your SRAD and the other one hooked up to the missile works. And one has, I'm just going to use an example, one would have 2 grams of powder in it, and the other one would have maybe up to 4 grams of powder in it, each having a single E-match.
So
So the way
that,
you could do this, you could have your the one you've already designed already in place, and you just have another E-match going to like a one of those centrifuge little plastic tubes with your black powder. And it shouldn't be
Yeah.
hard to implement. I'm sorry, Paul.
Yeah.
So are you saying we
No,
just partition inside this?
No,
maybe side by side with that cup you have, and you can even use a glove, you know,
the finger of a glove.
yeah, the finger of a glove, an E-match and a zip tie, and
Okay.
that's really
Yeah, sure.
simple.
Yeah, the other thing that's recommended, and I'll say it's recommended and people use their own choices. The majority of us now are putting our E-matches on top of the ejection charge, not on the bottom. And the reason we're doing that is that when the E-match goes off and it's on the bottom, it has a tendency to blow powder out and
Yeah.
not igniting the powder. If you put it on top, then it basically burns down and consumes all the black powder.
Yeah.
So,
Can we not push the E-match up higher till the piston?
yeah, you could, yeah, that's fine.
Yeah, we'll do that.
Yeah, that's easy to, now, for that ejection well you've got there, do you tape that lid down at all, or do you just depend on a pure friction fit?
It is a very good friction fit. Yeah.
I mean, you really want to contain that black powder as long as you can contain it. So, you know, it's, you know, you could almost take that, what you've got there, and remove the piston and just tape it. Put some wadding in, tape it down with some really strong tape like duct tape or something like that.
So you want us to
It will
remove this
blow the tape. It will,
piston
yeah,
completely?
just don't even that.
So
Don't
you don't
even
want,
use the top piece,
sorry?
just the top piece in your right hand.
Yeah, without this, or
Well,
just,
right.
You could, you could replace that with tape. And probably have a better black powder igniting than you do now. When you, since you've done some ground tests, is the inside of the tube really dirty with black residue?
kinda, not too much, but yeah, there are residues because of it.
Yeah, that's the black powder being blown by and not being ignited.
Okay. Mhm.
Thanks, Lee.
Yeah,
Okay, we'll
these are
try.
easy to,
Sorry.
yeah, these are easy to implement.
Okay, we will try doing that for our next test, and we'll let you.
Yep, it'll be fine. So you just put the powder in, you put some wadding, some paper on top to pack it, and I do a couple layers of tape over it, then tape around, and it'll keep it all in there. And that way you have a very positive control. Now you want to make sure that the tape is sticking to that metal, that it doesn't come loose. Some of my wells have gotten so dirty that the tape doesn't stick well. So you just want to watch that. But relying just on a friction fit for a piece of metal in that environment is probably relatively high risk.
Okay.
Yeah, I mean, there's a chance it could roll over and fall off. I mean, unless you had some way of securing it.
I like the idea. In
Yeah,
fact,
I do too.
Stuff and push things out, but trying to keep that black powder contained, because when it gets loose, it fails.
Yeah, we'll definitely look into it.
And then the full dual redundancy, just having another piece there with black powder and a finger of a glove or a piece of plastic, or easy to fix.
And your backup charge should be somewhere between 25% and 50% larger than the primary charge.
Yeah, sure.
Okay, is your SRAD computer set up to do Apogee deployment?
We do Apogee deployment through our primary SRAD, and the secondary SRAD that we had, that's just for testing. We've been trying out new stuff, and that is why it's going on there. The primary SRAD, like you asked, yeah, it does deploy the drogue at Apogee and also disreefs the parachute as it descends down.
Okay.
Your fins, I might have missed it. Your fins are aluminum plate. Is that
Yeah,
right?
there are many. Oh, by the way, the meeting might suddenly just end because I have a free plan. I'll just send the link again. I think it's better to just.
Are they airfoiled at all? Are they, I mean,
No,
are they
they're
gonna-
square cross section. Yep.
There we go. Okay. So I guess where we left off was that you'll be making changes for the Apogee deployment, adding a second charge well, which, and taking the approach, whether it's, as Bob has suggested, the finger of a latex type glove, or how it tape, or however you want to do it. That's great. The other thing is, for your charge well, to remove the lid and replace it with tape, and bring the E-matches up to the top.
Yep.
So we get a better combustion of the black powder. Beyond that, I'm not too sure I have too many more questions. Bob, are you?
I'm pretty good. I just sent an email. Wasn't sure we were going to reconnect or not. And the thing with the piston is, you know, I like to see new ideas. I don't want to discourage you from doing that. I just, my question was, have you tested that with the parachute and everything inside the rocket? I just wonder about that impacting the recovery system.
Yeah.
So I think the recommendation to leave it off is a good one. The only other questions I have, you know, rockets can sit out on the pads there for a long time. I would try and do a test on your altimeter batteries. Turn it on, let it run for 3 hours.
So we've done these tests. We've done the tests on our RC phase as well, and our primary flight computers as well, and also for our flight cameras. We've done battery drain tests, and we've gotten a battery life of around 8 hours, and there was a lot more of charge remaining in the batteries as well. So we can go well above 8 to 10 hours of battery life on these altimeters. And considering we won't be on the pad for more than 2 hours at max, it should be fine for everything. Even the RRC3s run for more than around 3.5 hours. That is on the 9-volt batteries.
Okay. Use fresh batteries, and probably somebody should
Yeah.
start a timer when you turn it on.
Yeah, we've done these tests. We'll be uploading all of these tests on a drive link, and we've documented all of these tests, and we've documented all of them, and we've put it in our design.
Okay.
Sure.
All right. I just want somebody to be watching it in case things are on the pad and it gets delayed, and you can say, no, we don't want you to launch. That's, potentially 3.5 hours or whatever. So just be aware of that. And the other thing, I know one of our teams recently had a problem with camera storage. Their rocket sat on a pad for a long time, and they had it running, and they filled up the SD card and didn't record anything. So use a big card if you can.
Yep, we've used big cards, and while doing the battery drain test, we also did a storage test for the cameras, and we get recordings of around 4 to 5 hours.
Okay, excellent.
Okay.
Good
Very
job
good.
testing.
Very good. Hopefully we won't be sitting on the pads very long, but we do have a lot of Rocketeers coming in this year, so it's and we have significantly increased the number of pads and so on and so forth. So hopefully some of those problems we had last year, and hopefully there's no rain, which obviously complicated things last year also. So
A little bit, yeah.
from that end of it. The only other comment I would make is double check all your recovery harnesses and make sure that there's no black powder residue, any signs of charring, all that sort of stuff. So you don't, so the safety reviewers at New Mexico don't decide that you need to change your harnesses out.
Yeah.
So beyond that, that was an excellent presentation. You answered all our questions. So I'm going to reverse the tables and say, what questions do you have for me? And Bob.
You had a question about
we have few questions regarding telemetry. So we couldn't actually test our telemetry system quite very well, and we were thinking of going with 900 megahertz and maybe 2.4 gigahertz. Due to lack of availability, we just went ahead with 2.4 gigahertz modules. We've been using the XB's S6B modules, which are based on Wi-Fi. The data rate on these modules are really good, but we were just concerned about the range on these modules. So is it possible for us to switch our frequencies once we come to the US, if we get hold on these 900 megahertz modules? Is it possible to switch frequencies after we filled out the frequency allocation form?
I don't know the answer to that. I would hope that there's room to do that for various reasons.
So are you asking for the ability to switch out something, or?
Yeah, so what we've done is we have a 2.4 gigahertz Wi-Fi modules. The only concern we have is the range. We've gotten around 3 kilometers of range, but we thought that we may require more amounts of range, which is why we might switch over to 900 megahertz modules once we arrive at the US, because we may order certain XB modules in the US and then test it over there for a week. So is it possible for us to switch between 2.4 gigahertz to 900 megahertz frequencies? Because there was a form which was which asked us about our frequencies on the telemetry systems. The SRAD one has 2.4 gigahertz, whereas the featherweight, it uses its 900 megahertz frequency. So I was just wondering if we could switch over from 2.4 gigahertz to 900 megahertz once we test the 900 megahertz modules in the US?
The answer is going to be yes, you can, but you need to make sure that you contact Da Vinci
Yeah.
and let them know your frequency changes.
Okay.
Okay, yeah, because Wi-Fi is not going to give you very much distance,
Yeah.
as you all know. So you really need to go to the not the MissWorks, but to the featherweight tracker, which is a lot of contestants are using. So it's very, very reliable. So yeah, but make sure that you've updated that form and that so they're in the loop.
Yeah, fine. Thank you.
Okay.
You guys.
Okay.
Yeah, we don't have any questions as of now. If we do have, I'll just shoot you guys something.
Okay.
Yeah.
All right. When you got the video ready, you can send it off to me, but that email is not going to. Can you post that video up on a shared link?
Yeah, we'll put it on a Google Drive link.
That'd be
Yeah.
absolutely perfect. And we'll figure out if we're going to post both of them or just one on that end of it. So, okay. You've got Bob's email. You got my email. You got any questions coming up? Howard, we're not bashful. And looking forward to meeting you guys and seeing you in New Mexico then.
Yep.
Yeah.
We'll see you there too.
You did a good job. Good testing. Looking forward to seeing you.
Yeah.
Thank
Yep.
you. Thank you guys. All right. Bye-bye. Good day.
Bye-bye.
Bye.